Hello, in this video we're going to go over some of the last problems from the AMC 2023 and this is AMC 12A. So these are the most difficult problems on the AMC, that's why I chose these. So I'm going to go over the last 4 problems. So the first one is there is a unique sequence of integers a1, a2, a3 all the way to a23 such that tangent of 2023x is written as a quotient of sum of tangents, powers of tangents. Whenever tangent of 2023x is defined, what is a sub 2023? The next one is let k be the number of sequences a1 through an such that n is a positive integer less than or equal to 10. Each ai is a subset of 1 through 10. ai minus 1 is a subset of ai for each I. And then they're asking us to find the remainder when k is divided by 10. The next one is how many ordered pairs of positive real numbers a, b satisfy this equation. And the last one, they gave us a function satisfying certain condition, and they're asking us to find f of 2023. Okay, so let's just start from number 25, which is the most difficult problem typically on the AMC. So as we have discussed in this channel, whenever we're dealing with trig functions, one of the best strategies is to use complex numbers. So let's look at tangent of 2023x. So this is sine of 2023x divided by cosine of 2023x. So both of these can be evaluated using e to the power of I theta. So if you look at e to the power of I 2023x, that is cosine of 2023x plus I sine of 2023x. And we can write this down as cosine of x plus I sine of x raised to the power of 2023. The real part gives us the cosine and the imaginary part gives us the sine. So let's expand this to see what we get. The parts that are real are 2023 choose 0, cosine to the power of 2023, plus the next part that is real is when you have I sine of x squared. So 2023 choose 2, cosine of x to the power of 2021, and then I sine of x squared. All the way to the last one that we have a real term is 2023. So the exponent of I sine must be even. So the last even would be 2022 cosine of x and then I sine of x raised to the power of 2022. So these are the real terms in that sum. The non-real terms, the imaginary terms, are 2023 choose 1 cosine of x to the power of 2022 times I sine of x all the way to the very last one, 2023 choose 2023 times I sine of x to the power of 2023. Now when we look at the tangent of 2023x, we get sine, which is the imaginary part, which is the part that has I. So that starts with 2023 choose 1, which is 2023, cosine of x to the power of 2022 times sine of x, and ends with 2023 choose 2023 I to the power of 2022 because I have to take out one of the i's, and then sine of x to the power of 2023. The denominator is all of the terms that are real, so it would be 2023 choose 0, which is 1, cosine of x to the power of 2023. All the way to the last term is going to be 2023 choose 2022, which is 2023, times cosine, then we have I sine to the power of 2022. Okay, so that's good so far. Now we will have to write this down in terms of tangent. So how do we turn these in terms of tangent? Let's divide the numerator and denominator by cosine of x to the power of 2023. if you look at all of these terms, the exponents add up to, the exponent here is 1 and 2023, the exponents add up to 2023. So if you divide the numerator by cosine of x to the power of 2023, you will get 2023 times tan of x. 2022 terms of cosine cancel with cosine of x to the power of 2022. One of them gives you a tangent. The last term is negative 1 to the power of 1011 times tan of x to the power of 2023 divided by, in the denominator, when you divide by cosine of x to the power of 2023, we get 1 all the way to 2023, and then negative 1 to the power of 1011, and then tan of x to the power of 2022. Going back and looking at the problem that they gave us, we have a1 tan of x, a 2023 tan of x to the power of 2023, 1 all the way to a 2022. So this is going to give us a1. This will be a 2023. This is 1 a0, and this one is a 2022. So the answer is negative 1 to the power of 1011, which is in fact negative 1. So the answer is negative 1. Let's look at the next one. Let k be the number of sequences a1 through an such that n is a positive integer less than or equal to 10. Each ai is a subset of 1 through 10. ai minus 1 is a subset of ai for all integers 2 to n. We are trying to find k mod 10. So the idea of this problem is very similar to one of the other problems that I have done on this channel. It's a Putnam problem. So let's use the Venn diagram and see what happens. So we have numbers 1 through 10 in this universal set, and then we have a1 here, a2 must contain a1, and so on, and then the last one is an. So this is a1, this one is a2, and this one is an. When we look at the numbers 1 through n, there are n plus 1 places that we can place every number. It could either go into a1 or a2 but not a1, or an but not an minus 1, or outside of all of these. So if we look at each of those 10 numbers, there are n plus 1 possibilities for each of the 10 numbers. So what does that mean? It means the number of these sets is n plus 1 to the power of 10. And then they told us n ranges from 1 to 10. Now, we are trying to find this one mod 10. If you're trying to find something mod 10, you need to find it mod 2 and mod 5. Let's find out what this is mod 5. So I can rewrite this one as n equals 2 to 11 n to the power of 10. When I write this down mod 5, I will get n to the power of 5 is the same as n by Fermat's little theorem. So Fermat's little theorem tells us that n to the p is n mod p for every prime p. So this is going to be n to the 5th squared, which is just n squared. N equals 2 to 11. Now, we have a formula for the sum of squares. It is n, which is 11, times n plus 1, which is 12, times 2n plus 1, which is 23, all over 6. But this starts from 2 and not from 1. So we will have to subtract 1 from here. Now if we take this one and evaluate this mod 5, we are going to get 1 here, 2 here, 3 here, minus 1, which is 5, which is 0. So the number that we got is in fact divisible by 5. Now we'll have to take it mod 2. So if we look at 2 to the power of 10 all the way to 11 to the power of 10 mod 2, there are 10 numbers in this sequence of numbers. 5 of them are even, 5 of them are odd. So this would be 5 then. So this is 1 mod 2. So we are looking for something that is 0 mod 5 and 1 mod 2. So the answer is then 5. Okay, so let's look at the next one. How many ordered pairs of positive real numbers a, b satisfy the equation 1 plus 2a, 2 plus 2a, 2a plus b equals 32ab. So the first thing that I did was I divided by 2. So I will get 1 plus 2a, 1 plus b, and then 2a plus b equals 16ab. Since we have only one equation and two different variables, it is very likely that we will have to look at some extreme cases. What does that mean? It often means using some inequalities and looking at the equality of that inequality. So let's apply, the first thing I applied was the AMGM, and then we will see if that works. So 16ab, which is the right side, is greater than or equal to. Let's apply AMGM to each one of these. And just to remind you, AMGM tells you a plus b over 2 is greater than or equal to root ab for a and b positive. So this would be 2 root 2a. So it's 2 times 1 times square root of 1 times 2a, 2 times the square root of 1 times b, 2 times the square root of 2a times b. Let's simplify this to see what we get. We have 2 times 2 times 2, that's 8, square root of 2a times 2a, that's 4a squared, and then we have b squared. And this is in fact 16ab. So interestingly, the equality happens. So when does the equality happen in AMGM? Equality happens when the two numbers are the same. So root ab is the same as a plus b over 2, if and only if a and b are the same. So we used AMGM for 1 and 2a. Equality happens when 1 equals 2a. We also used it for 1 and b. Equality happens when 1 equals b. And we used it for 2a and b. Equality happens if 2a is equal to b. So that tells us a must be 1/2 and b must be 1. And that value also works for the last one, which means there is exactly one solution to this equation. Let's look at the last problem, which is a number theory problem. Let f be the unique function defined on the positive integers such that the sum of df of n over d is equal to 1 when d divides n. And they're asking us to find f of 2023. Okay, so the first thing you want to do is, because we were talking about divisors, we will have to know the prime factorization of 2023. So that's 7 times 17 squared. In order to find f of that, we'll need to know f of its divisors. And just to rewrite the given assumption, this is what we had. We need to know f of its divisors. So we'll start from this scratch. We start from f of 1, f of primes, f of prime squareds, and so on. So let's look at f of 1. So if you plug in n equals 1, you will get f of 1 is equal to 1. This is for n equals 1 in this equality. If I call this one star, for n equals 1 in star, I get f of 1 equals 1. Now let's plug in n prime. So we will get sum of d divisor prime df of p over d. So there are two divisors for a prime. It's either 1f of p or it is pf of 1. So what does that give us? It gives us f of p is equal to 1 minus p. So for every prime, f of p is 1 minus p. Let's look at a prime squared. So if you look at prime squared, we get the sum d divisor prime squared df of p over p squared over d. This is 1. That gives you p squared f of 1, pf of p, and f of p squared. That's 1. We'll substitute, we get p squared plus p times f of p is 1 minus p plus f of p squared. That's equal to 1. And if we simplify that, we get f of p squared equals 1 minus p, because p squared and this p squared cancel. So f of p squared is also 1 minus p. So now we know f of 17 squared. Now let's look at f of pq. What is f of pq? We will have to do 1 f of pq plus pf of q plus qf of p plus pqf of 1. we know this is equal to 1. So we'll just substitute and see what we get. We get f of pq plus p times 1 minus q, q times 1 minus p plus pq is equal to 1. Now, we know that pq cancels here, and we are left with f of pq equals 1 minus p minus q plus pq. And this is in fact 1 minus p times 1 minus q. Now we can go ahead and evaluate f of pq squared, which is in fact what we are looking for. We can substitute n equals pq squared in the assumption that they gave us. So it gives us f of pq squared plus, there would have to be 6 terms because there are 6 positive divisors for pq squared. Pf of q squared qf of pq plus, so these are 3 of the divisors. Then we have pq f of q. Then we have q squared f of p. So these are 5. And finally the last one is pq squared f of 1. We know this would have to be 1. Now, f of pq squared is what we're looking for. So let's substitute the others because we found the others. So f of pq squared plus p times f of q squared is something we found before. That's 1 minus q plus q times f of pq is 1 minus p times 1 minus q plus pq times f of q is 1 minus q. F of p is 1 minus p, and then we have pq squared times 1 equals 1. Let's simplify and see what we get. So f of pq squared plus, this gets a little bit computational. I will give you a better method for this one, which requires a little bit of knowledge from number theory, but I'll talk about that after I'm done with this one. pq here and a pq here, they cancel. We have pq squared here, and we also have a pq squared here, so those two cancel as well. So let's just write down, I guess, the rest. We get p plus q times 1 minus p minus q plus pq minus pq squared plus q squared equals 1. Now, this guy gives you plus pq squared, that guy gives you minus pq squared. Let's put that in, plug that in to see what we get. We get plus p plus q minus pq minus q squared plus q squared is equal to 1. Q squared cancels, and we are left with f of pq squared equals 1 minus p minus q plus pq, which is in fact 1 minus p times 1 minus q. So finally f of 2023 becomes f of 7 times 17 squared, which is 1 minus 7 times 1 minus 17, which is negative 6 times negative 16. And that gives us 96. Now, I will give you a better solution for this one if you have some advanced knowledge of number theory. So how else can we do this one? If you look at the equality that they gave us, d divides n, df of n over d equals 1. This is a pretty well-known expression on the left. What is the expression on the left? The well-known expression on the left is called convolution. So this is a convolution, and that's just exactly the definition. This is the convolution of n and f. So this is what they gave us. Now, there is a way to evaluate these using inverse. So everything has an inverse. So you can multiply this one by inverse of n, and that gives you, this is equal to n inverse star with 1. That gives you n equals n inverse star with 1. So this tells us that f is in fact multiplicative. As I said, this does require a bit of advanced knowledge of number theory. So since it is multiplicative, it means f of pq squared is equal to f of p times f of q squared. So once you get f of p, which was 1 minus p, and f of q, which is 1 minus q, f of q squared, which is 1 minus q, then you're done. So this requires a little bit less work than the original method. So if you like this video, make sure you subscribe to the channel, and I will see you in the next video.